Welcome to this Physics Revision Explainer. Grab a pen because today we are absolutely crushing some tough numericals. Actually, we're zooming in on the real boss here, the question itself, how to read it, how to decode it, and ultimately how to conquer it. Let's get started. So be honest with me, does looking at a complex physics math problem give you a literal knot in your stomach? Well, you're definitely not alone. It's totally valid to feel anxious about this stuff because, honestly, these questions are literally designed to test our limits. They will absolutely trick you if you aren't paying close attention to exactly what the question is asking. But I love the mindset shift this source material offers. It basically says, take that fear, crumple it up, and throw it straight in the fire. Just burn it. We're going to use these specific strategies to level up and take on the absolute hardest questions head on. Okay, here's our game plan for today. 1. Rules of resistance questions. 2. Decoding complex circuit questions. 3. Mastering power and heating. And 4. Conquering light and lenses. Starting right off with section 1, rules of resistance questions. Okay, this first rule is a perfect example of why you've got to read the prompt super carefully. Exam questions love to ask what happens when you stretch a wire versus when you cut it. Now, think about it. When you stretch a wire to, let's say, 3 times its length, you aren't just changing the length. You're squeezing the wire, right? You're making it thinner. So the cross-sectional area actually drops to 1/3. And since resistance is length divided by area, a 3 times increase in length combined with a 1/3 decrease in area multiplies the total resistance exponentially. It jumps by 9 times. But if the question says you simply cut the wire in half, the area stays exactly the same. Only the length halves, so the resistance just halves. Reading the specific wording of the question here is literally everything. Now, here's a detail that always trips people up. Resistivity. No matter what the question says about stretching, cutting, or bending the wire, resistivity never ever changes. Why? Because it's tied to the actual material itself, like whether it's copper or iron, not the physical shape. Keep that rule locked in your mind. Moving right along to section 2, decoding complex circuit questions. All right, let's hit some rapid-fire hacks for these chaotic webs. Rule 1, current stays constant in a series circuit. Rule 2, voltage stays constant in a parallel circuit. And Rule 3, which is my favorite, current is incredibly lazy. It will always take the easiest possible path out. So if a question presents a short circuit, meaning a path with 0 resistance, the current will take that path and completely bypass any resistors in its way. All those bypass resistors, you can just cross them out. They become mathematically totally useless. Okay, let's pivot to something that frequently ruins practical exam scores, reading an analog meter. To nail this, you've got to understand the least count. That's really just a fancy way of saying the absolute smallest value a scale, like a voltmeter, can accurately measure. Let's walk through this step by step like a real calculation. Let's say your question shows a voltmeter where 10 tiny divisions equal 1.5 volts. Step 1, count those divisions. Step 2, divide the value by the divisions. So 1.5 divided by 10 means your least count is 0.15 volts for every single tiny tick mark. Step 3, just look at where the needle is pointing. If it's resting on the 12th tick, you multiply 12 by 0.15 and boom, you get a reading of 1.8 volts. Super easy once you know the exact steps. Oh man, you've got to be so careful with graph questions. These are absolutely designed to catch you off guard. Always check the axes. In a VI graph where voltage is on the y-axis, a steeper slope equals higher resistance. But if the question pulls a fast one and flips it to an IV graph where current is on the y-axis, a steeper slope actually means lower resistance. So before you even glance at the lines, analyze the question's axes. All right, section 3, mastering power and heating. Let's pause and really look at this exact super tricky scenario from our source material. If a question tells you the current flowing through a conductor is doubled, but the resistance is decreased by 4 times, how much more heat is produced? Just think about that for a second. The answer? The heat stays exactly the same. Let's break down the math. The formula for heat is I squared RT. When you double the current to 2I, you have to square that whole thing, which gives you 4 times I squared. That 4x multiplier perfectly cancels out the divided resistance of R over 4. 4 divided by 4 is 1, right? Leaving you right back at your exact original amount of heat. Okay, here's another classic trap question that catches almost everyone off guard. If current increases by 100%, what is the percentage increase in power? Seriously, take a guess.
The answer is an unbelievable 300%. Yes, you heard that right. 300%.
So, the crucial point here is understanding how percentages work in these physics formulas. 100% current increase means the current simply doubles. And like we just saw, squaring that doubled current makes the new power 4 times the original amount. But, and this is a huge but, the question asks for the percentage increase. To find an increase, you take the final value, subtract the initial value, divide by the initial, and multiply by 100. 4 minus 1 is 3. So a 4x total power output means the actual increase from the original is 300%, not 400%. Always answer exactly what the question is asking.
And finally, Section 4, Conquering Light and Lenses.
First, we need to quickly summarize refraction. Optical density basically dictates both the speed and the path of a light ray. A higher refractive index means you're dealing with a denser medium, which means a slower speed of light. And when light moves from a rarer medium, like air, into a denser medium, like glass, it will always bend toward the normal line. Now, when questions ask you to calculate those exact angles using Snell's law, it usually looks like a terrifying nightmare of fractions. But here's an incredibly simple hack to set up the equation without getting confused. Step 1. Just take the sine of the incoming angle. Step 2. Multiply it by the refractive index of that exact same side, medium 1. Step 3, set that whole thing equal to the sine of the refracted angle multiplied by the refractive index of medium 2. Just remember, side 1 equals side 2. Let's actually see this in action. If light comes from air, which has an index of 1, at a 60-degree angle, you just multiply 1 by the sine of 60, which is root 3 over 2. So that side equals root 3 over 2. Now look at the glass side, which has an index of root 3. To perfectly balance this equation so the right side also equals root 3 over 2, the sine of the refracted angle has to be 1/2. And what angle has a sine of 1/2? 30 degrees. It perfectly reveals the answer without any messy fraction manipulation. Lastly, let's talk about combining lenses. If a question ever asks you how to combine lenses to achieve zero optical power, don't panic. It's just simple addition. You literally just mix positive diopters with equal negative diopters. For instance, combining a +2 diopter lens, a +8 diopter lens, and a -10 diopter lens gives you a grand total of 0. It effectively neutralizes their focusing power completely. All right, we officially have the problem solver's playbook. We know the hacks, we know the traps, and we know exactly how to read what a question is truly asking us. So, with pen in hand and that fear thrown straight into the fire, I've got to ask, what's the very first question you're going to dismantle today?